fait plaisir d'accueillir Gary Lupyan aujourd'hui, qui est professeur de psychologie à l'université de Wisconsin-Madison. Il a eu son doctorat en 2007 à l'université Carnegie Mellon sous l'encadrement de Jay McClellan, de renommés réseaux neuronaux, suivi des postdocs en sciences cognitives, neurosciences cognitives à l'université Cornell et à l'université de Pennsylvanie. Au centre de ses intérêts de recherche se trouve la question de savoir si et comment notre cognition et notre perception sont augmentées par le langage. La langue, c'est quoi qu'elle fait pour nous? D'autres intérêts de recherche majeurs ont porté sur des effets descendants, ça veut dire top-down effects, sur la perception et ainsi que sur l'évolution du langage, l'iconicité et les causes de la diversité linguistique. Les langues adaptent-elles à différents environnements sociodémographiques? Maintenant, quelques mots en anglais. Gary Lupyan, most of you know him as a professor of psychology at University of Wisconsin-Madison. He obtained his doctorate in 2007 at Carnegie Mellon with Jay McClellan. He did postdocs in cognitive science and cognitive neuroscience at Cornell and at Penn. At the center of his research interests is the question of whether and how our cognition and perception is augmented by language. We'll find out what's meant by augmented as well as what's meant by telepathy in a few moments. What does language do for us? Other major research interests have included top-down effects in perception, evolution of language, evolution of language has been a big topic here at UCAM. We've had summer schools on it. Iconicity, which is the degree to which symbols resemble their reference or are connected causally to the reference, and causes of linguistic diversity. Do languages adapt to different socio-demographic environments? And with that, it gives me pleasure to, and I have to tell you all, je vais le dire en français, faites vos questions dans la liste de chat, et puis Gary, qui est jeune et a beaucoup de traitements parallèles, il va regarder. Peut-être que je vais tirer son attention aux questions qui sont urgentes. Put your questions in the chat, and Gary will spot check the chat, and I'll draw his attention to something if I think there's something that he missed that he might want to talk about. But with that, I hand it over to Gary Lupyan.
Thanks for the introduction, and thanks for inviting me. I can't see your videos if they're on, so if you want to turn it on and show whether you're pleased or displeased or surprised or bored, that can be helpful. All right, so in preparing the talk, I realized that rather than titling it From Whorf to Telepathy, a more apt title is From Telepathy to Whorf. Telepathy is where I'll start, and it's an odd beginning, but one that I think nicely sets up some of the questions that will follow. It's a thought experiment. Is telepathy in principle possible? And of course, its popularity in science fiction, and before that, even in, for example, writings of Mark Twain in a letter, saying, why shouldn't some scientists find it possible to invent a way to create this condition of rapport between two minds at will? Then we should drop the slow and cumbersome telephone and say, connect me with the brain of the chief of police at Peking. So you can see some of the assumptions at work here. Language is this slow, error-prone, communicative interface. And if only it were possible to just directly connect our minds, how much more efficient and faster that would be. Here's a similar, more recent proposal by Mary Gell-Mann. Someday, for better or worse, a human being could be wired directly to an advanced computer. And by means of that computer to one or more other human beings, thoughts and feelings would be completely shared with none of the selectivity or deception that language permits. Because of course, not only is language often thought of as slow and error prone, but it's so easy to deceive with, right? These assumptions that this is something that is in principle possible are also at the heart of Elon Musk's Neuralink project, right? Building just such an interface to allow human to machine and human to human direct interfacing in a really fun to read. I can share a link if people are curious about it. It's a visual essay by Tim Urban from his visual essay blog, Wait But Why. Here's how he presents some of the basic ideas of this Neuralink project, the digital brain. Right now, communication between machines is, of course, very fast, in part because they're wired through wires that are much faster than neurons, right? So computer to computer, super fast. Computer with itself, super fast. Human with itself, well, not as fast, right? This is the speed of thought. And then when you have to communicate either to machines or to other humans, now we're in the land of slow, serial, error-prone language, right? And so this idea that bandwidth is the limiting factor, and while, you know, we probably can't ever communicate between one another as fast as computers can between one another, there are certain limitations that we probably can't go through, we can at least bring us all, bring human to computer communication to the speed of thought, right? So language here is a bottleneck, right? It's a problem. And if we could bypass language, we could communicate at the speed of thought. So I'm going to, just to foreshadow, I'm going to argue that there's a fundamental problem with this assumption. Just to bring us also kind of more up to speed, last week, I think Jan LeCun, who is, of course, one of the most influential AI researchers of our time, head of AI research at Facebook. So he recently tweeted, language is an imperfect, incomplete, low bandwidth serialization protocol for the internal data structures we call thought. Okay. So my goal today is first to convince you that this thinking is mistaken. We're going to start by identifying the root cause of this language as problem assumption. So why would people from Mark Twain to Jan LeCun think this way? There's a reason. I'll show you a bunch of evidence suggesting that this assumption is wrong. So we're going to present lots of empirical data, some more data that language helps human minds to be interoperable. So to the extent that people can align their mental states well enough, at least for lots of kinds of communications, not without error, I'm going to argue that this is in part made possible by language. That language is not the problem, it's a solution. And I'm going to end by speculating on a stronger claim that it is, to quote DeMillo et al., it is through language that our minds become general purpose. So let's start. At the root of this language is the problem assumption is the assumption that words just map onto pre-existing concepts. And this is, I think, it seems to be quite prevalent in computer science and AI, but it's somewhat prevalent in cognitive science psychology as well, less so than before. But here is, let's unpack this assumption. So one way of viewing the problem of word learning is as mapping. So on this view, a child enters the world. They have some innate pre-existing knowledge, perhaps, but they're also certainly learning a lot from perception, from interaction. They form certain categories through this interaction. And then depending on the language they happen to be learning, many of those categories will have names, and the names on this view are mapped onto these already existing conceptual categories. So an especially strong proponent of this view historically has been Lila Gleitman and many of her colleagues. From one of their papers, the meanings to be communicated and their systematic mapping onto linguistic expressions arise independently of exposure to any language. The meanings can, of course, arise from specific experiences. She's not, although she is, quite Fedorian, she's not arguing that, all these concepts are innate. But importantly, she is arguing that you can't really learn a word for a category you don't already have. Languages differ in their vocabularies. This is not in itself a problem for this view. The way to deal with it is, well, a lot of our categories we don't have names for, right? Unless we happen to speak a language that has a word for it. But importantly, on this mapping view, whether you have a word for something or not, or how easy it is to express in a particular language is irrelevant, because, it's relevant for communication, but certainly not for thought, for reasoning, for anything nonverbal, okay? And so once you buy into this assumption, it helps you hold what might appear to be a contradictory view. So for example, here is from Pinker's language instinct. On the one hand, Pinker makes, I think, uncontroversial observation that it's amazing that we can move our mouths, right, or move our hands if we're speaking a signed language, and we can reliably cause new combinations of ideas to arise in each other's minds. Remarkable, right? But on the other hand, also Pinker, in the same breath, the idea that language shapes thinking is ridiculous, seemed plausible when scientists were in the dark about how thinking works. Right? And so these two statements are not contradictory if you assume that language is just a medium of communication. Sure, you learn lots of things through language. If you learn that Picasso died in 1973, you probably learned that from someone telling you that or reading it, not from any personal experience. So that's important, although I think somewhat underestimated, but that's not a controversial statement. But your conceptual repertoire, your cognitive chunks, that on this view is pre-existing. Language has nothing to do with it. What's an alternative? The alternative is to actually just think of language as another form of experience, and a very ubiquitous form of experience for pretty much all humans. So to quote Jeff Ellman, words might be thought of in the same way that that one thinks of other kinds of sensory stimuli. They act directly on mental states. They don't map onto meaning, they're cues to meaning. And so if we think about our semantic or conceptual knowledge, and we use those terms somewhat interchangeably here, as a high-dimensional space, manifold, it's informed by innate core knowledge, direct experiences, perceptual experiences, motor experiences. Grounding really matters, right? It's also informed by language. We learn from language, and not just, I'm going to argue, things like when Picasso died, but language is informing us, is helping us form our basic and building blocks of thought. Interestingly, much of the literature on semantic knowledge and psychology omits entirely learning from language, focuses somewhat on innate and on direct learning from direct experiences. And also another thing that figures quite prominently in it is learning through inference. And we can touch on that later on, what I think of it. Right, and so if you learn that a penguin is a bird, you ascribe to it other features of birds, right? And so now you know things that you didn't necessarily observe or were told. So if this is starting to sound like linguistic relativity, a bit of Whorf, yes, it is, right? One of the Whorf's most famous quotes, right? He's basically arguing this, that the categories entitled isolate from the world. He had this, right? He was writing this in the 30s, 40s. This is before even George Miller's work on chunking, right? So the term chunk didn't really exist. So he talked about isolates of experience, but these are basically cognitive chunks. And so he's arguing that we don't find them because they stare every observer in the face. They are constructed. And according to Whorf, a major way in which they're constructed is by learning a language. So let's just, because I'm not sure how much you guys know about, where Whorf's place in sort of pantheon of cognitive science, psychology, and linguistics, but here are a few recent observations about the extent of linguistic diversity. Right. The reason this is important is one might expect that if languages are very strongly constrained by pre-existing chunks, then yeah, you should find differences, cross-linguistic differences, because our experiences differ depending on the culture, the physical environment. You wouldn't expect a language to have a word for an animal that doesn't exist in your environment. But you would also expect that lots of sort of basic categories would exist universally, that there would be lots of universal meanings. Turns out that they're very hard to find. So here's a paper from a couple of years ago in which the authors went to 20 different field sites, 20 languages, including some signed languages, and they gave people various stimuli to name: colors, shapes, tastes, smells, textures, and sounds. And here they're quantifying how codable these various stimuli are. Here's a triangle. How much do people in this language agree on what this should be called? Here's here are various colors. How much agreement is there? Smells, tastes. The author's original main goal was to test this old idea that comes to us from classical Greek writing, that there is a universal hierarchy of codability, that smells are sort of ineffable and tastes are, a little bit less ineffable, but shapes and colors, those are real, those are universal. And that's why it's easy to talk about them. And so is this hierarchy actually observed? Well, it's observed in English, a few other languages, but although on average smells are less codable than other modalities, pretty much every violation of this hierarchy is observed. Okay, tastes, you might wonder, why are tastes so codable? This is only the 5 basic tastes, and even so, English speakers have a hard time recognizing that this is sweet, this is salty, this is umami, and so on. Okay, so you find that in some languages, tastes and textures are more codable than colors. Some languages, colors are extremely hard to describe. If you look at pairwise correlations, this is colors, but you get similar data for other modalities. Are colors that are easy to name in one language also easy to name in others? Not really. I mean, they're mostly positive. These are not very high correlations. And if you look at the source of differences, it's not the case, as is often thought, that some languages have many finer grained categories, while other languages have fewer, larger categories. That you do find that. But what you find a lot of is just cases like this, where a lot of the color space is relatively well named in English, but you look at other languages and there are parts of the color space that just are not named, right? There's no consistent way of naming it. What do people do when you give them, if you give a Lao speaker one of these colors? Well, they don't, sometimes they say, I don't know, but most often they produce something, and that something is usually a specific word, like, oh, that's the color of X, right? And it turns out that this is a bad recipe for alignment. You might think that, people agree on what the color of a lemon is. So if you call something lemon colored, you're going to agree, but actually no. Across all modalities, what the best predictor of alignment, of codability, is whether the language has an abstract term. So a big reason why English speakers don't really agree on smells is that for most English speakers, apart from certain domain experts, there are really no abstract smell words in English. There are words like bad, stinky and fragrant, but those are just affective terms. Perfumers and wine experts have more specialized vocabulary and they do better, at least within their domains. But in some languages, everyone is an expert because, as Asfa Majid and her co-authors argued, because in part, they have to learn this system of abstract words as a child, and they use them. Do some categories stare every observer in the face? Okay, people vary on these, perceptual things, but surely there are words that just align really well across languages. So in a recent paper, we used the distributional semantic model in about 40 languages and about 1,000 meanings to see how well different semantic domains were aligned across languages and what predicted alignment. And the results are not what really anyone expected. And we validate this with human ratings and with various norms, so it's not just an artifact of the method. The most aligned domains are quantity, time, and kinship. So number words, 5 in one language means 5 in other languages. That's nice. You'd expect that. Time, so again, Monday, Tuesday, March, February, yesterday, tomorrow. There is cross-linguistic variability there, but these are pretty structured systems, and they're structured in many of the similar ways across the languages we looked at. Kinship terms, another very structured domain. But while animals, for example, align reasonably well, these are concrete things, they really exist out there, make sense. Many other concrete meanings, various common artifacts, plants, agriculture, vegetation, clothing, motion, right? Basic actions, walk, run. These don't align very well. An interesting finding is that for both concrete and more abstract word meanings, what matters, what predicts whether the meanings will align across languages is phylogeny, are the languages related, but controlling for phylogeny, how related the languages are non-linguistic measures of cultural similarity. So this is from the DPlace, and that anthropological database that codes for similarity of cultures across many dimensions, the subsistence, the kind of technologies they have, the kind of inheritance patterns, kind of food. And so cultures, even if they are in very distant and speaking less related languages, the extent to which they align on those cultural features, they tend to have words that are easier to translate. So there's a lot of perhaps much more cross-linguistic diversity than one would expect if we just pick up sort of the joints of nature and then map words onto them. All right, so does it matter? Why might one think that it matters whether you have a word for something? Well, one reason why it might matter is that it is through learning words, not only through that, but partly through learning words, that we are forming our cognitive chunks. So even for formal domains like, 10 times 10 is 100. But 100 is a better chunk than 10 tens, right? And aunt is a better chunk than mother's sister, or father's brother's wife, right? So a word is not quite its definition, even for these formal categories. So let me show you, now we're going to get some empirical data. Let me show you a straightforward experiment showing that even small differences in nameability in educated, enculturated English speakers really matter for what seems like a formally very easy problem. So as we already talked about, some colors are easier to name than others, and there is quite a lot of consistency within a language group as to which colors are easy to name. So for example, if you ask English speakers to just free name these colors and compare that to free naming these colors, you find that you have about 80 to 85% agreement in a free naming task. And the people who don't agree they're coded as not agreeing because they specified something more specific. They specified a particular shade of orange, red, and so on. And then for these colors, people produce all sorts of things. Notice that it is often a more source, mustard, right? So it calls up some specific item rather than an abstract term. And when it is an abstract term, this is clearly not gray, but as it happens, this is the modal label for this color, but it's only produced by 6 to 10% people. So people produce lots of things. There's not much agreement. So there's a clear difference in nameability here. Does it matter? So here's a very simple task, a supervised category learning task in which participants see stimuli like these, and they have to drag it into category A or category B, and they get feedback, letting them know if they got it right or not. And we do this a bunch of times, see how well they learn these categories. The categories are very simple, especially when you see all the items together. Members of category A have a red spot here. Members of category B have a brown spot here. These categories are formally, logically identical, except they're made up of colors that are harder to name. Now, in the published paper, there are 5 studies that together control for all sorts of perceptual confounds. There is a difference in saturation here, we control for it. But it turns out this doesn't matter because all of these colors are very easy to discriminate. So perceptual factors are not playing a big role in this study. And yet, despite the simplicity of this rule, just one condition you have to figure out, the more nameable colors, these categories made up of more nameable colors, are learned much more easily. This is a very robust effect. You can replicate it within subjects. So one might think, okay, once you learn the high nameability category, now oh, it's this kind of rule that I'm looking for, and that should really help you learn the other ones. And so they should, after a very short time, they should converge. And after a while, they probably do, but at least, after 50 trials or so, they don't. So here's a replication, same thing. It's not just a color thing. So we can control for low-level perceptual factors better with shapes. So here are some shapes, novel shapes, but that in this arrangement, these are called Tangrams. They remind many people of various objects, so they're more nameable, more meaningful in this case. Now you can take them and just rotate them, and now these are less nameable. And here too, it matters. So I don't want you to leave thinking that colors are special here. This is the claim, that this is a more general phenomenon. Do easier to name things make for better cognitive chunks? At least in this kind of study, yes. Our working hypothesis here is that the reason they help is that they make for better hypotheses. So when a person, this is an explicit task, people are actively trying to figure out, what is the rule? And a rule like the red versus brown, or it's about redness, is more likely to be posited by our subjects. And then once you posit it, it's pretty easy to confirm whether it's correct or not. Now, on this more traditional view on which words just map onto pre-existing concepts, there's a prediction that, once you learn the word, what it does is it activates this concept. And, whether you see a dog or you hear a word dog, it's sort of the same thing at some level, because they both kind of point to this same, on traditional views, amodal kind of symbol dog. And I'm going to argue that is also wrong, that words play a role not just in the initial learning of categories, but even after you learn these categories, they affect how this knowledge is activated in the mind. Why might it matter? It matters because of the unique relationship labels and other verbal language more generally has with the world, with its reference. So consider the relationship between dogs and their barks, okay? The fact that dogs bark is, as far as humans are concerned, arbitrary, right? If dogs meowed, we would learn that dogs meow, right? But the fact that some dogs bark at a low pitch, other dogs bark at a high pitch, that's not arbitrary. That's quite systematic, right? That's constrained by bioacoustics and physics, right? And that goes for inanimate objects as well, right? And we learn these mappings. And so we learn that big dogs tend to bark with a lower pitch and small dogs with a higher pitch. And so a bark, even if you easily recognize it as being a dog's bark, it's motivated by certain physical properties of the dog. Now let's look at words. Words as sort of indices work in the same way. So words are motivated by properties of their speaker. So you can distinguish with high accuracy, you know, whether it's a male or female who is saying the word dog. You can tell their age. You might be able to tell something about where they're from the pronunciation. So there's a relationship, a systematic relationship between the word dog and the speaker, but there's not really much of a relationship between the specific instantiations of the word dog and the different dogs, right? It's not entirely true. We routinely do things like say dog in a lower pitched voice when referring to a bigger dog when talking to a child. So iconicity is turns out to be surprisingly large and you know, recently more appreciated feature of language. But nevertheless, the principled way in which language is distinguished from all of these linguistic cues, from these non-linguistic, non-verbal cues, is that they can break free of this motivation. All right. So the form of the label is not motivated by the referent. And so this leads to a hypothesis that words will activate conceptual categories in a different way from other nonverbal cues, namely in a more categorical way. And so here is a very simple experiment that was designed to get at that. So in this study, on each trial, people hear a word, like the word guitar, or they hear some nonverbal cue that we norm to be readily identifiable, like the sound of a guitar. Then there's a delay, and then there is a picture, and it will either show a guitar, in which case people say yes, or something else, like a dog, in which case they respond with no. Now, of course, every guitar sound, right? Every picture of a guitar isn't necessarily a picture of a specific guitar. And every guitar sound is a sound of a specific guitar. So you can talk about an acoustic guitar and electric guitar, but you can't have a picture of just a guitar, and you can't have a sound of just a guitar, right? And so this allows us to use this kind of design where we compare how good people are at verifying whether the picture is correct or not after hearing guitar versus after hearing a sound. And we can see, okay, let's match a classical guitar to a classical guitar and an electric guitar sound to an electric guitar sound and see how that compares and how the word compares. Okay, so here is how long it takes people to correctly recognize the picture of a guitar after it's followed by an incongruent sound. So this is hearing an electric guitar sound followed by a picture of a classical guitar. The task is it, you know, at the basic level, like, is it the right category? So that's how long it takes. And if the sound is congruent, it takes less time. So this shows that people are tracking this information and they're using it. Okay, and you get the same thing for dogs and for motorcycles. So people have a lot of this kind of perceptual knowledge. What about the label? What about just hearing the word guitar? That has less information. It doesn't tell you what kind of guitar that it is, but that's precisely what you want, because for this task, it doesn't matter, right? The goal is to activate the category to the best extent you can. And when we look at that, it takes people less time to recognize guitar, right? When they just hear the word guitar, right? And it's not just about guitar, it's about lots of categories, okay? So the way to interpret this pattern is that the word is activating a more categorical representation, allowing you to more efficiently recognize the picture at a categorical level. We've done various studies, I won't go into the details here, showing that this label advantage is not a kind of late semantic level effect that has to do with a congruence between the word guitar and the picture as compared to the sound of a guitar and a picture. Rather, you find a difference between the label. So this is the N400 component here, signaling kind of violation of expectations at a later semantic level. And both labels and sound show the same strength. N400, where you see the difference between labels being cued by a label versus a other kind of sound, nonverbal sound, is in relatively early perceptual processing, particularly in the left hemisphere, starting within 100 milliseconds of stimulus onset. So there's a perceptual locus of this effect, such that even after 100 milliseconds, these early initial responses to electrophysiological responses to the pictures are modulated by the previously presented label. So within that first 100 milliseconds, these early visually evoked waveforms allow you to some extent distinguish between whether the picture matches or mismatches the cue. But for sound cue trials, you can't do that until later in the trial. Is this just speed? No, it's not. So if it were, it would still be interesting, just not as interesting. It's not just about speed. It's about the kind of representation that is activated by the label. Specifically, I've argued that the label activates a more categorical representation. What does that mean? One way to operationalize that is that the label selectively activates category diagnostic features, the things that make a dog different from non-dogs, the things that make a guitar different from non-guitars. That predicts that this effect should be especially strong for typical objects, because they're most congruent with what is activated by the label. And so we can look at it in several ways. Here's from the same kind of study, hearing a car, the word car or a car starting sound. People, of course, are faster to recognize more typical cars compared to less typical cars, but this typicality gradient is stronger when you've been cued by a label. Okay. And this general effect that the label kind of evokes a more typical representation is surprisingly general. So cars, they certainly they don't have necessary and sufficient conditions. You can find, you can reasonable disagreement whether something is a car or a van, okay? But a triangle is a triangle, right? So they look different, but they have a definition and an easy to verify properties. And people know this, right? So what's a triangle? It's a figure with three sides, angles that add up to 180 degrees, shape with three straight sides. So people know what a triangle is. So you might think it doesn't matter whether you activate their knowledge of a triangle using the word triangle or using some other way. And here, the other way is also linguistic. It just doesn't use the label. But it turns out it matters. So if you ask people to draw a figure with three sides, they draw triangles, makes sense. Here are the kind of triangles they draw. If you ask people to draw a triangle, they also draw triangles, but they are systematically more similar to one another and more typical. What is a typical triangle? we'll see in a moment. How can a triangle be more typical? Well, people think that some triangles are more typical than others. Isosceles and equilateral triangles with a horizontal base are the most triangulist of all, according to people. And it's not just a pragmatic effect. You might think people in this task are thinking something like, well, if they meant for me to draw a regular triangle, they would just say draw a triangle, was a figure with 3 sides. This difference is quite automatic and implicit. So in a similar kind of speeded recognition task, if you cue people with triangle or 3 sides, and then people see triangles of various configurations or rectangles, and they have to verify that, yes, this is 3-sided or is a triangle. For atypical triangles, there's not a label advantage, but for these more typical ones, there is. Right? So the label cues you to be a better recognizer of these more typical versions of the category, even for these formal categories. Okay, so let's take stock. Stephen, I'll get to your question about what makes something more nameable in a bit. Yeah. At the root of this language as a slow serialization protocol way of thinking is, I think, the assumption that language just maps onto thoughts. Okay, and if we bypass it, take it as just an intermediary, we would be better off. Right. And the problem with this view is both that language, I would argue, is a major source of our concepts. This idea of words are a big source of our cognitive chunks. And it's also, as these experiments I just talked about mentioned, is a way of very efficiently activating category diagnostic features. This is not always a good thing, right? There are many tasks in which the category of something is irrelevant or gets in the way of what we want to know about the thing or how we want to represent it. And in these cases, language can impair performance. But when the task is categorization, when it's I'll show you a kind of formal reasoning, we do want to represent things in a more categorical way. And of course, having a more categorical representation allows you to more easily compose. Okay, so the experiments I've presented so far already hint at this idea that mental states activated by language are more similar to one another. There are more ways to be atypical than to be typical. So if you're making things more typical, you're converging. Okay, but let's see that idea tested in some more direct ways. Okay, so this is more recent work. Here's a task. We generate some novel shapes. Okay, these are the prototypes that we start with. They're meant to be hard to name, but easy to visually distinguish. We then perturb them to create a sort of prototype structure with more and less. So as they go out here, these are getting more different from the prototype. But as you can see, these categories are easy to distinguish from one another, but they remain hard to name. And we're going to familiarize people with the distributional structure. So the idea here is that we created these two prototypes so there is objective coherent covariation in people's environment. There are two categories that cluster together. They're not really confusable. Okay. But we're going to name them. We're going to teach people labels for them in one group, but not in another group. So here's a familiarization just to get people to associate labels with these stimuli and also to get them to just familiarize them with the ways in which these stimuli differ. So it's just a simple match to sample task. One of these stimuli appears. In a label condition, it's labeled. people never see the prototypes, they just see the distortions. There's a short delay, then they see one that exactly matches the one that they saw, the sample, and one that doesn't, and they have to respond right or left, which one matched the sample. After this, we give people the stimuli and ask them to sort the stimuli. And now we also include the prototypes, but these are labeled A's and B's just for your benefit. Participants don't see the labels, of course. And what we want to know is how many clusters do people form and how similar the clusters are between people. Okay, now, first, let me show you the kind of clusters people form, namely whether items within categories are placed closer together than items between categories, right? And everyone should be doing this because this is in the visual structure. And indeed, everyone is doing that. Even people who haven't, the baseline condition is people who have not seen these stimuli prior to the sorting task. But as you can see, people with labels show a more categorical difference. So they are clustering items with labels within category, all the gecks closer together and all the talps closer together. The people who observe these stimuli with labels are also much more likely to form only 2 clusters. Okay. And most interestingly, controlling for the number of clusters people formed, their clusters are more similar to one another. So to the extent that these clusters are sort of a proxy for one way of measuring kind of their mental states, right? The sort of representations activated by these shapes, the group that was exposed to these category labels, even though there's no communication involved here, produced more similar clusters. Last bit of data, I think. We've also been looking at individual differences between people's reliance on language. So this is an emerging field. For pretty much any domain you measure, people differ. And some of those differences have been recognized for a long time and others less so. So for example, visual imagery has been recognized and studied for over a century. It's known that some people have very vivid visual imagery and other people, many people's imagery is quite vivid. Some people have no visual imagery whatsoever. It turns out the same is true of inner speech. Some people experience it all the time. Other people never. Most people quite a bit, and so the never people are in the thinner tail of the distribution. It's not just about inner speech. This is a more general difference about people's subjective reliance on language, how likely they are to cue a memory with language, for example, versus in other ways, right? So self-generated language in order to cue, previous memories, for example. And so when you ask people about it, when you have people comment on it, you have people make statements like this, right? And others like that. In some previous work, we quantified these differences by creating a new questionnaire that asked not just about inner speech, but in the same questionnaire, we asked about visual imagery, manipulation, orthographic. This is a surprising kind of thing. Some people, it's not that common, but some people report to routinely imagine orthography. So the printed forms of words. Other people, many people never have this experience. But you can see visual, verbal. This is a common thing for people, and importantly, counter to some myths, there is no trade-off here. So it's not the case that some people are sort of more verbal and other people are more visual. The people who have lots of visual imagery tend to also be the people who experience lots of inner speech and who use language to kind of manipulate their mental thoughts. we'll just focus on this verbal component here, so we can have people do a task and see if where they are on this verbal dimension, this languaginess, this propensity to verbalize, predicts some interesting things. What we're going to measure in this study is how the similarity of people's mental states as judged by the drawings they produce to a verbal cue. So the idea here is that someone who routinely kind of uses language to guide their thinking, whatever thinking is, those individuals should be more similar, should be more categorical and more similar to one another. Okay, so the task is we're going to cue people with 4 superordinate categories: draw a piece of furniture, draw a reptile, draw a dessert, draw a kitchen appliance. We're going to give them, I think they had 1 minute, maybe 2 minutes to draw. It's amazing what some people can produce in a minute. These are, look at this couch. It's amazing. Reptile, dessert, kitchen appliance. So 200 participants, each 4 drawings. We have 800 drawings. Some people draw much better than other people. So we obtain for each drawing a measure of how well drawn is it, whatever it is, how well drawn is it. There's people have pretty high agreement on these. And then we can measure other things. So we can measure nameability. So name this thing. So controlling for drawing quality, the thing on the left and the thing on the right differ. So the thing on the right, everyone names as a fridge, refrigerator. The thing on the left, it could be a bunch of things. Okay, so less nameable, more nameable. Are more languagey people drawing more nameable things? Again, controlling for drawing quality. I should mention it does not, this languagey measure does not predict drawing quality. But controlling for it, yes. Small effect, but yes. Do they draw more typical things? Compared to furniture in general, how typical is this drawing? We have people rate all the drawings. Again, yes. Small effect. All of this was pre-registered, so we're not fishing around, and we've replicated it. It replicated as a very small effect, but yes. As you might expect, if they're drawing more nameable things and more typical things, are they drawing more similar things? Here we used a combination of both automatic visual similarity measures from a convolutional neural net trained on ImageNet. Turns out to be pretty good at predicting people's visual similarity ratings of these kinds of drawings. So how similar is this snake to all the other snakes? Here, right, to compute all the pairwise ratings, that would require way too much data. That's why we're relying on this more automated measure, but we do validate it. And we find here a difference in the expected direction. So people, regardless of verbalization, are not any more or less likely to produce, for example, a lizard when cued with a reptile, but the kind of lizard they produce is more typical and more similar to one another. So there is a lot greater alignment, on at the basic level. Okay. So learning labels yields more aligned mental states. And then some preliminary initial evidence, much more work needs to be done here, that conceptual representations of people who naturally rely more on language, according to our subjective measures, appear to be more similar to one another. All right, so they're aligning. So lastly, I just wanted to speculate on this stronger claim that it is through language that our minds become general purpose. So this is a view that's been at various times advocated by, for example, Andy Clark, Dan Dennett. It's a view that is probably most in philosophy opposed to the thinking of Fodor, for example, right? So on Fodor's view, our minds are compositional, they're symbolic. We have, at the extreme position is all our concepts are innate. And it is those properties that allow humans to learn language in the first place. But we can flip that around, right? What if it's learning language that makes us at least, somewhat symbolic and somewhat compositional in our thinking? So it's a compositional thought and symbolic thought is not a cause of language, but at least in part its consequence. And this, of course, speaks to classic issues in cognitive science. What sort of computing device is a brain, right? So here's a sort of classical view that is, weirdly still pervasive in modern thinking in AI, despite the ubiquity of neural networks. All right. So I'll present one little last bit of data for you. It's sort of a cute little experiment. You can read the whole, the full thing in a published paper if you want. But here's the idea. If we are naturally good at symbolic thought, you might expect that people shouldn't commit the kind of errors that I'll show you that they do. We're going to go back to triangles. People know what a triangle is. 100%, only 18 people, but this is more generous. Confirm, yeah, that all three-sided polygons are triangles. Yep, that's true. But a lot of people at the same time say that that's true. And they say that some triangles are better triangles than others. And you ask them, what do you mean? They say things like this. So yes, they know the definition, but it seems that our psychological representation of a triangle, it's not quite definitional. And this has consequences. So if you give people a bunch of triangles and ask them to click on all the ones that are triangles, it shows the proportion of errors. These are obviously triangle. But for, whatever, 15% of people, these are not. And what predicts it with a correlation of 0.9 something is their typicality. This pervades our inference as well. So all triangles have angles that add up to 180 degrees. Please select the shapes below that you think have angles that add up to 180 degrees. Okay, this proportion of errors. Pretty much everyone selects these, and people are leaving these out. Okay. You ask them why? It didn't look like it. Okay. So the paper has more of these kinds of cute studies. So we're showing even educated people have trouble. Education, turns out, doesn't predict performance in these tasks. Have trouble following the simplest of rules. Now, what does that mean? Well, the fact that they can do it at all, which is more than you can say of other animals and of young children, it speaks to our power of symbolic thinking. But I would argue that it is language and symbolic culture more generally that is allowing us to do this at all. And the fact that this is surprisingly difficult speaks to the sort of, that this is going against kind of our biological nature, right? On its own, our minds are not that good at it. And so for good reason, we've invented systems to allow us to do these kinds of tasks, okay? And so to bring this back to telepathy, I would argue that we've already invented this condition of rapport. For general purpose rapport, it is natural language. And for specific kind of rapport, for math, for symbolic logic, for programming computers, we invent other systems, right, that allow us to communicate in a more precise way, right? But in all cases, we can't assume that we are interoperable, that we have all the same units, right? And that if only we could circumvent these cultural systems, that our units would just naturally align, right? So, maybe we'll at some point invent telepathy that is mediated by these systems, but arguably, right, it wouldn't be as big an advance, right? It would just be kind of a faster version of texting. Thanks.